I met this subtitle today because Alessandro was talking about discrete-time port-Hamiltonian systems based on discrete gradients. And well, we did this and we exploited it for control based on symplectic integration. And I talked with Peter Betsch 2 days ago that he presented in his generic talk different possibilities. He did energy, momentum, entropy conserving integrators, but he said also in his community there are people who are doing completely different things. There are people who are doing symplectic, the other ones doing energy preserving, and then they have long discussions on a metaphysical level. But this is just to say that there are different possibilities where we could define discrete time effects in port-Hamiltonian systems. And I prepared this talk, but the work which we did in the last 2 years was together with Laurent, which you see here, teaching on discrete-time port-Hamiltonian systems. By the way, there's another important person. There's Thomas Elie also on the picture, who works in that field in musical acoustics, which you might know. And then there are Tobias Thoma, who is also here, and Christian Martens, who collaborated during their student works and PhD respectively. So I would like to start with a little scheme, or this is the point of departure, which shows the class of systems I'm looking at. So I'm looking at explicit port-Hamiltonian systems in continuous time. And I look at the equations, well, it's like an explosion sketch, yeah? Because the backbone of the port-Hamiltonian system representation is a relation between power variables, yeah, which corresponds or which represents well, a subspace where power continuity holds, power conservation holds. So, and we can express, for example, in this form, the interconnection conditions of such a finite dimensional Dirac structure, where the flows and the efforts are power conjugated variables, such as also the inputs in the sense of control and the outputs here are power conjugated variables. Okay, so this is the core or the backbone of the port-Hamiltonian system representation, and then we have to add several things. But before we add something, we observe that from the skew jointness of this representation, J, I missed it here, J is obviously a skew-symmetric matrix, and in this talk all the matrices J and G, they are assumed to be constant to have the simplest possible case. Yeah? So there's a skew-symmetric relation between the effort and flow variables from which we directly can deduce that there is a structural power balance on that subspace. And if we now complement this these relations by dynamics, when we say, okay, the flows are nothing else than time derivatives of a minus sign of the states, and constitute the efforts, the co-states, they are derived from a Hamiltonian. If you plug this into the structural power balance, we come up with what we know as the differential energy balance, which shows us passivity, in this case losslessness, because I forget about R, yeah, for the moment. Everything can be also added by with dissipation, but here it is much clearer to expose it without dissipation. So we end up with H dot equals Y transpose U, which we all know, which shows passivity and losslessness. Well, in this kind of systems, you know that we can obtain them in different ways, basically from port-based compositional modeling, and the class of port-Hamiltonian system gives rise to control methods which are at least inspired by energy as a concept to prove at the end stability of equilibria, etc. And now there are two questions which could arise when we look at this in a continuous time setting and if we want to go to discrete time. So one question is, what is a reasonable definition for a port-Hamiltonian system in discrete time systems? Well, and now we can dispute what is reasonable. And I thought, okay, reasonable in our eyes was that first this representation should somehow retain this modularity of the continuous time counterpart. And then we found it attractive that we can reuse, well, just as with the discrete gradients, methods which are well known in Hamiltonian systems. This means which give us back some reasonable behavior when the inputs are zero, when we have a closed system. And then, of course, we need to have some idea about the approximation errors we are making in terms of the power flows. Okay, and this would be a good tool if we have such a kind of definition to do some energy consistent modeling in discrete time and simulation or co-simulation. And then the second question is, based on this, is there also an implication on control design? Is there also, or more precisely, is there an implication of the implementation of controls and sampled control loops? And this will be, these two questions, they will be discussed during this talk, and they are based on some works we have done together in the past years. And I will give you a little overview on that. Of course, there is a huge literature, and only a part of this is just snapshotted here. Yeah? Generally, symplectic integration is something very old. Yeah? People were wondering how to do the simulation or the numerical approximation of Hamiltonian systems at a celestial scale or at the molecular level. Yeah? And this leads to, for example, the Sturmer-Vallée scheme. Yeah? As an example for a symplectic integrator. Then variational integrators, which are also widely used in discrete time optimal control, they are symplectic by construction. And, well, as another keyword, you can also use symplectic algorithms if you want to solve two-point boundary value problems, for example, in optimal trajectory generation, just as some points. And of course, there has been quite some work also on the definition concerning port-Hamiltonian systems and concerning discrete time energy-based control. As usual, it's an incomplete list, but to mention some keywords, very early it was tried to give some generic definition of a discrete time Dirac structures and port-Hamiltonian systems. Then in the field of robotics, Stefano, of course, one is interested in connecting controllers in discrete time, sampled controllers with continuous time physical systems in an energy consistent manner. Yeah? And this can be done. Then discrete gradients are widely used, for example, in the field of musical acoustics, but there are also, we discussed with Laurent, in the work of Rémi Müller, they don't want to find discrete time approximations, but they want to have really continuous time signals, which are approximations of the models they have. And well, also discrete gradients have been used in several works, for example, in mechanical IDI-PBC for energy-based control. And there is also quite recent work, which is also based on a bit on older work, which takes sampled system models which are based on series expansions in conjunction with a generalized sampling mechanism. So there's a lot of work to be done, which has been done. And okay, then what we did together with Laurent is basically we looked at, okay, how can we, what can we do if we look at symplectic integration schemes? So the remainder of the talk is basically we have two parts. First of all, I would like to present you the definition we developed and which we thought is useful, together with some critical remarks on that. And then I will show you how this can be used for control.
Yeah.
Sure.
Because for me, it's just okay. You have your Dirac structure,
Yeah.
that there is no time in
Yeah.
the Dirac structure. So what's the problem to bring discrete time? I just take. So where is the?
Yeah, maybe.
So where are you after? But maybe
Yeah, you will see it probably here. We have the structural power balance, which is, for example, which is satisfied in every point of time. Yeah. When we go to sampled systems in a digital control loop, then there's a natural way that we go from this point-wise representation in time to an energy balance per sampling interval. Yeah. Because in control you have maybe one measurement and one instant where you impose your control law. And then you let the system run over the time interval of fixed length. Yeah? But I hope this will become clear. Yeah? So that's a bit of a collection of the requirements or from which we deduce the steps we have done. Yeah? If we take our picture here, then as I said before, we would like to conserve this kind of the Dirac structure, and we want to derive from that some structural balance equation, which then is an energy balance per time interval. And then we know that, okay, this will be a numerical algorithm, there will be some discrete time dynamics, and this discrete time dynamics which will give some error, of course. This is somehow clear. And then, as I told you, for the case where u equals 0, we want that, well, the energy shall be conserved, which is true for the discrete gradients. But okay, keep in mind that we will see it later in symplectic integrators, there's something different. There's a modified energy which is not too far away from the original energy which is conserved. And then here we have some dashes, and we will come to these dashes at the end of that part. Okay, first of all, Hans, you asked me, okay, what about symplecticity? Yeah? And then I said, okay, let's wait for Thursday. Then I give one slide where I give an idea why this is important, or why we should do, if we go for Hamiltonian or port-Hamiltonian system, symplectic integrators. So this is, from my knowledge, let's take a 1D Hamiltonian system. Then it has this particular structure of the Hamiltonian vector field. We recognize this skew-symmetric matrix. And then Hamiltonian systems have a very nice property that the Hamiltonian flow, so the solution which is induced starting from an initial value, it is such that areas in the phase plane are conserved, or if you go for higher numbers of degrees of freedom, well, some hypervolumes. Yeah? So these areas are conserved. This means if I start here, for example, in this kind of square, then the flow, the solution of this Hamiltonian system transports all those points to other points, but they make up an object which has the same area as the initial area. And if you look into the book by Heira, then you see cats which are deformed in several ways. Yeah? But they are not getting bigger, not getting smaller. They are only deformed. And then, okay, there's something else. And how could we characterize this area here? Well, I took a square. Well, this square, and assume that it is spanned by these two, it could be a rectangle, it is spanned by two vectors. Yeah? If we want to get the area of this square, we can take the determinant of the matrix which is given by these two vectors, and this can be expressed, well, something like this skew-symmetric bilinear form. And this is nothing else than the application of what is called the symplectic form, the exterior derivative of that Liouville form Bernard was talking yesterday, applied to these vector fields. Yeah? And what is very nice, which makes a bit the link between energy conservation and symplecticity, at least a bit on a phenomenological level, is that if you like, you can express the energy conservation of a Hamiltonian system, because you see the J appears here and here in terms of the application of the symplectic 2 form, where two times the same covector, and this gives 0. So this is for the symplecticity. So it is a property which is fundamental for closed Hamiltonian systems. And then at a certain point I was asking, where does this word symplectic come from? Yeah? And I found in this book of Hermann Weil about the classical groups, there's a chapter to the symplectic group, and then he writes that the symplectic group is defined as the set of all linear transformations under which a given non-degenerate skew-symmetric bilinear form, which we have seen there, remains unaltered. And then later on this page there's a footnote where he writes, okay, he wanted to call this group complex group, but then there was a confusion with the complex numbers. Yeah? So he decided to call this, to take the corresponding Greek adjective, which is symplectic. I find quite a funny story. You can read this in this book. Okay, and now we're going to integration, yeah? And we stick with one-step integration methods. And a one-step integration method is symplectic whenever the method is applied. A numerical one-step method is called symplectic if the one-step map is symplectic. This means area conserving in that sense whenever the method is applied to a smooth Hamiltonian system. And there's a bunch of examples, and in this talk we will stick to the implicit midpoint rule as the simplest of the one-stage Gauss collocation schemes. Well, implicit midpoint rule, most of you will know it by heart, how to integrate a system with this, an initial value problem with such a rule where we take a midpoint value for the state and at the midpoint time. And then we can either, well, compute the midpoint like that, dividing xk and xk plus 1 over 2. Well, or equivalently, it turns out that we can simply do a half backward Euler step with tk plus 1/2 to obtain this midpoint value. And this can be expressed, this red prescription can be written in terms of a Butcher table. This means, well, implicit midpoint rule and the other methods which we will be talking about can be expressed in terms of Runge-Kutta methods, which makes it somehow easy to write them down. And then I told you that the symplectic methods have a property, if applied to Hamiltonian systems, other than the discrete gradients, they don't exactly conserve the Hamiltonian, but they will conserve a modified Hamiltonian. Something which is, so the evolution of the discrete time system will be such that in the sampling instant, it equals the solution of a continuous time system, which is not too far away from the Hamiltonian system we are looking at. And for an example of the linear oscillator, well, we might construct this modified Hamiltonian, and it turns out that the modified Hamiltonian is the old one plus something, well, which is here a series expansion in H, and when we see that here 2k, this means for k equals 1, we will have 2, it will be the first error term, and by this way we can, for example, using so-called backward analysis, determine the order of the method of the corresponding method. So this is an important message. The modified Hamiltonian for the closed system is conserved under a symplectic integration scheme, not the original. And this is just for information. When we take different structure-preserving or not structure-preserving schemes to integrate a nonlinear Hamiltonian system, this is a simple one with 2 degrees of freedom, a constant mass matrix, and some potential energy to the power of 4, some toy example. Yeah? And we simulate it from an initial value. We see, well, the Euler forward and backward, they do something non-conservative in their corresponding direction. The discrete gradient, here I use the midpoint discrete gradient, it will keep the energy exactly. The implicit midpoint rule, the red one, well, will not keep the exact energy because we have drawn the exact energy here, but I would be able to draw a line if I draw the modified energy here. And a bit the same with the trapezoidal rule, which is not symplectic but conjugate symplectic. So also somehow good. Yeah. Maybe we can look at this later, because then I will be running out of time. Okay. Actually, okay, you had the other discrete gradient, but I can show it to you, yeah? Okay. Now implicit midpoint rule, and let's go to the generalization of that to higher orders. This is a Gauss-Legendre collocation. So we have a collocation scheme, and what does it mean? Here again, we have an initial value problem, and we start at xk0 means the first value at the sampling interval. And we want to find a polynomial approximation of the solution such that, well, it coincides with the initial value. Good. And that the slope, we are in 1D, yeah, that the slope to the solution, well, corresponds to the right-hand side of the differential equation if we substitute the polynomial approximation. So we have the collocation conditions here. And then, well, we can, for example, to parameterize these polynomials or to parameterize better the time derivative here, we can use, if we like, Lagrange interpolation polynomials of degree here s minus 1. Because this is x dot, so x tilde will be of degree s. Well, and the Lagrange interpolation polynomials, we have to use collocation points. And these collocation points, if we use Gauss-Legendre collocation, they will be the roots of some shifted Legendre polynomials, etc., etc. And if we have done so, then we have this polynomial approximation of x tilde dot. We could integrate this in order to get the integration step. And when we do the integration, then we end up with something which can be written as a Runge-Kutta method, because there will be terms which will be the integrals over the Lagrange polynomials. So just as a setting to come from the generalization of the implicit midpoint rule to Gauss-Legendre collocation. It is a family of S-stage integration schemes with the highest, which are implicit, with the order 2s. But okay, we want to use this for the definition of discrete time port-Hamiltonian systems. So here I accelerate a little bit in order to also be able to show something with control. But the key idea, and we can also discuss afterwards, is that we take the power variables. It's one idea, different possibilities are there. We take now the power variables, effort, flows, inputs, outputs, yeah? And we assume we are looking for solutions in the space of polynomial approximations. And these polynomial approximations, we parameterize them with the Lagrange polynomials. This leads to, and this is maybe to your question, Hans, by the property of collocation polynomials, this leads to the fact that in the collocation points we have exactly the same Dirac structure. Yeah? But we have, well, on an interval S different collocation points, so we have to use all this information on the sampling interval, so we need to stack all those Dirac structures on that interval, and then we can write it like this with bigger matrices. We can construct a product or so. So the nice thing here is that the core of what we will be doing is a Dirac structure in terms of discrete time variables, which has the same matrices. It's blown up. Yeah? As a difference to maybe to the discrete gradients where J and G, they will be modified. Okay, and then what I told you, from this pointwise power balance, we go now to a energy balance per sampling interval. We take the polynomial approximations, integrate this power over the sampling interval, substitute, and we get something like now energy products in terms of the discrete power variables, where M is, denotes that there is some kernel or some matrix which is made up of the integrals of those L's. And then we have this, and the nice thing is if we substitute the structure equations from the last slide after exploiting some calculation rules, it turns out that this thing again is 0. Yeah? So this is the first brick of this definition of discrete time port-Hamiltonian systems. Another brick is, okay, which comes naturally from using the polynomial approximation with the Lagrange polynomials. Well, we can take f, the polynomial approximation of the flow, and we integrate it in order to obtain x starting from an initial value. This returns us the discrete time dynamics, which is expressed in terms of a Runge-Kutta integration step with the coefficients as shown before. And then there's a point, of course, we have to now do something with the constitutive equations, and at that time, well, one possibility is to simply evaluate the constitutive equations on the degrees of freedom of this polynomial approximation. We did that, yeah? Some critical remarks on that later. And when we do so, what drops out is that, well, we can write down this kind of discrete time energy balance if we like. So this is a bit of misuse of a notation, yeah, because here it was defined that this delta hk, this increment, well, it is the approximate integral of this power, yeah. But this is basically not the difference between h at the end of the interval and h at the beginning of the interval, yeah. This is this here, this increment, and this is typically what we would like to have to be 0 if the system is closed, yeah, or would we like to be equal to the energy product of inputs and outputs. This is equal in the talk by Alessandro when we use the discrete gradients, yeah, for u equals 0. But here it equals only, or this error vanishes only in the case of linear port-Hamiltonian systems and with Gauss collocation, which has been stated clearly before. Yeah? So there's no surprise. Yeah? And here again, I remind you, this is, but when we're using symplectic integration, this is also nothing which we can expect in a general case, because we would expect that if u equals 0, we would have here delta h bar modified equals 0. Well, and this brings us to what we have defined as a discrete time port-Hamiltonian system based on symplectic integration, where we have a discrete time Dirac structure, we have a discrete time dynamics, we have a structural energy balance which can be derived therefrom, but we have a generally inexact but somehow consistent with the scheme discrete energy balance. Then, okay, some thoughts here, as I mentioned, if U equals 0, then if we would take here the modified energy in the constitutive equation, we would have an exact energy balance. But okay, do we want to always construct the modified energy function for an arbitrary nonlinear? I don't know. So these are questions. What are the possible implications if U is non-zero? Yeah, we could construct a modified output. A question is also what is the consequence of the type of interconnections. We haven't discussed this too much so far. Yeah? If we interconnect on the level of the Dirac structures, well, basically no problem. 5 minutes. Oh, you're strict. Yeah. So there are many questions. Okay, but finally we have to do something with control, and the idea was, maybe the motivation, we take, here we have such a two-link robot, which we have seen frequently, and we do something bad with him. Yeah? We use an arbitrary, I think, PD plus controller here, and we want the tool center point to draw a circle. But we impose by control a very high control stiffness, and we use a very long sampling time. So what the poor robot does, don't know if you hear the sound. I make the sound taka 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 taka. Not what he should do, yeah? Okay? And they're okay. Maybe this is not the typical use case, but we could have systems where really we have a high control dynamics with a relatively low sampling time, yeah, if we go for microstructures, for example. Yeah. Okay, so this is the setting in a typical, here for a mechanical system control loop. We have a continuous time mechanical system. We have this frequently zero order hold, so we have some input shaping mechanism which shapes the control signal per sampling time. We sample, typically at equidistant sampling times. In mechanical systems, it is simple to get the positions. We somehow have to reconstruct the velocity. And the larger the sampling time is, the larger is the mismatch between the control model if we neglect the sampling mechanism and if we do what is frequently done, which is the emulation controller or quasi-continuous implementation. And well, we have shown that if we take symplectic integration, not restricted, other one we could have seen. If we take this as a basis to describe both the model and the target system in a coherent manner, then we obtain a control loop with only minimal modifications which we will see right now. 2 minutes. Yeah? The idea is simple. We don't do discrete time control design, but we do discrete time control implementation. So we go ahead and say we derive a controller, a nonlinear general controller in continuous time. And we would like to use this also in the sampled control loop. Well, if we had the Lagrange interpolation polynomials, then an idea which imposes that, okay, we could also use them to shape the input signal. Already you see that it might be not the best idea at the end. But still, to reuse Gauss-Legendre collocation, we could have the idea to use this type of signal shapes for the input to obtain second order, fourth order, sixth order approximations of the controlled plant and the desired behavior. Well, and then, don't look at the slide, but then we basically do numerical integration of the open loop system. We do numerical integration of the closed loop system. And the key is now that we compute those stage values for the states based on the target behavior of the closed loop system. Yeah? So we make a prediction step with the closed loop dynamics, and we use the stage values of this prediction step to implement our control law to parameterize. Here are the stage values of this Lagrange interpolation type input. We use the same value, the same control law, evaluated in the predicted stage values to parameterize the generalized input. And this works if, well, h is not too far away. So if this assumption, if you want to discuss this, then we can do it after. But this assumption is satisfied for reasonably small sampling times. And this is what I meant before on the slide with minimally invasive. If we do so, and here for the implicit midpoint rule in a mechanical system, we have the same picture as before. Here's the sampled system with all this mechanism. We have the same control law we have derived. Only what we do is we substitute the arguments in the control law by the corresponding predictions. And the predictions, they can be done, well, in this red box here. Yeah? So the solution of a nonlinear system of equations, which we can do in every time step, and which we can do also if the order increases. Yeah? And what is also nice, if we have a mechanical system, and this is just a remark, if we reconstruct from those stage values the velocity, then the interpretation of what we get out is a kind of generalized Sturmer-Verlet scheme, which is somehow beautiful, at least. Okay, I skipped this slide, which tells only that we can do this type of control implement. No, I don't skip it. Control implementation with different types of integration schemes. Yeah, we can do it also with discrete gradients. We can do it with the trapezoidal rule, etc., etc. Well, what changes is only where the structure of the control law. Yeah, in the one you have two evaluations of the control law. In the discrete gradient, we have to compute the discrete gradient. Basically, we have to solve another system of equations. Yeah. And well, in the implicit midpoint rule, you reuse the control law and substitute other values. One remark, well, sometimes when in these papers we wrote symplectic discrete time control. Of course, the closed loop, maybe this was a bit catchy, but of course we cannot expect that the closed loop, if we do only energy assignment, energy shaping, would behave conservative, yeah? Because what we do is we use an approximation of the open loop system, and we don't take any other measures to make it really conservative, if you like, in an energy shaping step. And this is the result. Oops. And then I really skip the slides. This is the result if we apply now this very simple technique to, at the beginning it shapes a little bit, shakes, but then it does what it should. It stops, okay? So you see, we went to the boundary or the border of the dynamics, yeah? It's not what is healthy for that robot, yeah? But, oops, sorry. Here you see the difference in the control signals which you would have heard, yeah? This is in the emulation controller, this is with our controller, and if we use some filtering, there's another scale, yeah? So the magnitudes are even smaller. So if we take what I said before, if we take the difference quotient of the stage values and filter it, and accordingly, then it behaves much nicer. Just as a picture that if we go, forget what I've written, but if we go to these boundaries of the operation domain, high sampling times, high dynamics, then there will be really a performance increase, in particular in the control signal, which will be not that oscillating. And the very last point, which is that, okay, I mentioned that this was implicit midpoint rule, so it was Gauss-Legendre with one stage. Yeah? We can reuse this, or we can do basically the same thing based on higher order Gauss-Legendre collocation. And we did it in the lab with this floating ball, and it should switch from one to another distance and should make like this, and we go for high sampling times. If you use the emulation controller at a sampling time of 10 milliseconds, there will be it will be destabilized. With the zero order hold, we can go up to in the experiment. In the simulation, it's even more, yeah. But in the experiment, we can go up to 25 milliseconds. But we see actually here what is the problem with Gauss-Legendre collocation if we apply it for the control loop. You have really ugly, very ugly control signals which are highly discontinuous. Yeah? or what? Okay, we could have expected it because we used the Lagrange interpolation polynomials. But the good message is, the remedy is that we use something different. We use spline or Hermite interpolation, and actually this works as well. I did the computations yesterday. So we can go, we have at least a tool at hand which allows us to implement continuous time controllers at high sampling times. So I presented that symplecticity is not only an interesting property to do long-time simulation of Hamiltonian systems, but we can also exploit it to give one definition of discrete-time port-Hamiltonian systems, where some questions remain. We can use it, Gauss collocation, but also other integration schemes in a very straightforward way for control implementation. And in that field, we have kind of future ongoing questions which are relied with the interconnections, with more generalized sampling methods, observer design, etc. and etc. I thank you for your attention, and I don't want to miss the hint on our French, German, Dutch, but this is in brackets, doctoral college. It's paid by the French-German University. But it's a doctoral college which is organized together with Bernard Maschke and Jacqueline Skerpen. It started this year. Some of you maybe are waiting for emails. I will respond after I'm back. It is a series of workshops every half a year, basically, plus the possibility to get some support for doctoral mobility. So if you want to be together more with us and your fellow PhD students, then check the websites and or write an email, and we will be happy if you are interested and if you join. Thank you very much.
So if you take what you've constructed there and put everything, efforts and flows together and get a discrete times version of the system, xk plus 1 is something of xk, where does the gradient show up in that, where does the Hamiltonian show up in that formula?
Mm-hmm. At that point, the Hamiltonian, that's a nice thing about this, yeah?
Yeah, that's why.
That at that level, the Hamiltonian does not show up. It's just an interconnection of currents and voltages, forces, velocities, yeah? The Hamiltonian pops up if we substitute, if we want to integrate, yeah?
Yeah.
Then we have to close the equations, yeah? Then we have to need some increment of x here, and we need to compute the E, and this is done here in our first step based on the evaluation of the gradient of the Hamiltonian in the stage values.
So would that mean you could write down a formula for the discrete evolution which has the Hamiltonian somewhere directly, explicitly inside?
I can do it. For the moment, I can do it if u equals 0 and if I know the modified energy here. Then I can do this.
Okay.
Then this is an open question for me. What happens if there is a u? Yeah? Then the construction of the modified system is not yet clear to me. Yeah? Okay. And what the implication then is for interconnection of really physical systems. So this is work to do.
Yeah. Okay, thanks.
Thanks.
I see that there is still some question, but I'm sorry we must postpone this for the coffee break, because now it's time for the next talk.
Thank you very much.
Thank you.